कनेक्टेड है। हाँ, क्यों, क्या हुआ? अरे कनेक्टेड है। Yeah, good evening everyone. We will start in next 1 or 2 minutes. I'm just waiting for some other people to join. Otherwise, we will start by 6:05. Yeah, okay. We will start. If somebody joins in between, we will let them join. So, uh, good evening. I'm Rahul Chaudhary. I'm a PhD scholar in IIT Madras, and I'm also a NPTEL PMR of NPTEL TA for this course, EMI, EMC, and Signal Integrity, which is taken by Professor Amitpa Bhattacharya from IIT Kharagpur. So this is fourth session of live problem solving session. Here I will be solving few problems which are related to this last week's lectures, and the idea of this session is to help you understand the problems and help you solve the problems which are there in the assignment. So the problems will be similar but not the same. And if you have any doubt, please unmute yourself and you can ask whatever doubt you have. So we will just go through the brief summary first, or like what have been discussed in the previous week. So first, professor has discussed about the resolution bandwidth of a spectrum analyzer. So this is what a spectrum analyzer looks like. So it's one example of a spectrum analyzer. So what a spectrum analyzer is a device which is used to measure the intensity or the amplitude of a signal between a frequency range. So, and then what is a resolution bandwidth? Resolution bandwidth is the, so just to this is a snapshot of a data sheet where they have discussed about the bandwidth, like they have mentioned what is the resolution bandwidth for this amplifier, sorry, a spectrum analyzer. So its range is given as, and this bandwidth is minus 3 dB. Sometimes it's 6 dB bandwidth, is minus 3 dB bandwidth. So it's from 1 hertz to 3 megahertz in 1 by 3 sequence. So what resolution bandwidth is? The resolution bandwidth of a spectrum analyzer is the width of the intermediate frequency filter, determining its ability to distinguish between closely spaced signals. So it's just one textbook definition. What actually it means is, if there are two signals or two frequencies in a signal, let's say one is like this and then the other one is, now if in this signal there are different frequency components, so this is my frequency axis. So if different frequencies are different intensities, just a second. So yeah, we have just started right now. We are discussing what is the topics, what are the topics that have been discussed in the last week by professor. So the first topic in the lecture 16th, I guess, was resolution bandwidth of a spectrum analyzer. So I was just mentioning about what spectrum analyzer does and what is the resolution bandwidth of a spectrum analyzer. So if you go for a very low resolution bandwidth, then the price will increase. So those are very sensitive equipments, means like if there are two frequencies which are closely spaced, if the resolution bandwidth is very low, it can easily able to find it out, like it can able to show what is the spectrum, like what are the energy content in that particular frequency. If it is higher, like the resolution bandwidth is higher, it won't be able to resolve between the two. It will give a mean kind of like a sum up value of those two frequencies. So if we just go with the textbook definition, what a resolution bandwidth of a spectrum analyzer is, the resolution bandwidth of a spectrum analyzer is the width of the intermediate frequency filter. So, and there is a filter, intermediate frequency filter. If this width is very less, then it is good, because if you see in the lectures, professor has made some windows in the between three frequency components, and when if it is if that window is falling inside the two signals like f1 and f2 or fa fb, then whatever that spectrum analyzer is giving is a sum up approach of that. It's not the particular intensity value or amplitude value of that particular frequency, it's a summed up thing. So the resolution bandwidth of a spectrum analyzer is the width of the intermediate frequency filter, determining its ability to distinguish between closely spaced signals. And then in the next lecture, professor has discussed about radiated emission model. That's why we were discussing about some antennas, right? Like Hertzian dipole, and which is a current element, and a dipole, and what are the E field and H field at a far field distance, because there are two ranges of an antenna. If it's a near field and far field, so the far, if it is at a far field, if we are discussing at a far field, we can consider that antenna as a point source, and whatever the E field and H field are coming, we can use the generalized formula. So that's what we have discussed. But if it is in the near field, we can't just use a generalized formula for that antenna. We can't consider it as a point source. So, but yeah, 1 second. So we can't consider that as a point source if it is too close to the, if it is not in the far field range. If it is in the near field, but we won't be discussing about those near field characteristics, because we are not concerned about them in EMI EMC. So we are concerned about the radiated emission model right now. So this is just a small summary of what has been discussed. Now we will start with the problem solving session. So question, and I request you, if you have any doubt, please unmute yourself and ask me. And one good thing would be, like, if you are you can have a pen and paper with you along, and you can start solving the problems. I will give you sufficient time. I will also go slowly, so you can also yourself solve the problems, and if you face any difficulty while solving or any doubt, small doubt also, you can just ask me. So this is question number 1. Question number 1 is, what is the minimum resolution bandwidth of the spectrum analyzer according to FCC for the measurement frequency range of 30 MHz to 1 GHz for radiated emission, and according to CISPA 22 for the measured frequency range of 150 kHz to 30 MHz, and this is for conducted emission case. So if you have any doubt, just ask. Otherwise, you can unmute your, mute yourself. Okay. So first of all, it is talking about two things: FCC and CISPR. What they are. So FCC is, if I just note down, like wrote down this full form of FCC is, FCC stands for FCC. It stands for Federal Communications Commission. Federal Communications Commission. It's a US based organization. So Federal Communications Commission. So, and this CISPR 22, it's a IEC standard. Mostly in Europe they follow this IEC standards, and in US they also follow this, but their main concern is whatever the regulations made by FCC. So according to FCC, sorry, this is FCC minimum spectrum analyzer bandwidth is so they have differentiated based upon the frequency range. So like now we are talking about the radiated emission. So in the question they are asking about 30 megahertz to 1 gigahertz for radiated emission. So in radiated emission measurement frequency, if it is in the range, so here they are asking about 30 megahertz to 1 gigahertz. If this is the measurement frequency, the resolution bandwidth, I am just writing RBW, resolution bandwidth of the spectrum analyzer should be at least 120 kilohertz. So this is a standardization body that have mentioned this. So it's kind of a fact that you should be remembering it. Like I can't just explain it why 120, why not 110 or 1 or like 100 kilohertz, because this is the minimum. At least this much should be there, and if the signal is above 1 gigahertz, then the resolution bandwidth can be 1 megahertz also. So this is for radiated emission from FCC, and now CISPR 22 for they have asked in the question, it is asking about what is the minimum resolution bandwidth for conducted emission where the measurement frequency is 150 kilohertz to 30 megahertz. In that case, the minimum frequency of that spectrum analyzer or the resolution bandwidth of that spectrum analyzer should be 9 kilohertz. So conducted emissions are those emissions or those unwanted signals which are traveling through a conduction or conductive wire, let's say a metal strip in a PCB. So that is what a conducted emission is. A radiated emission is which is radiated by something, let's say one antenna, but this is unwanted radiation that we don't want. So this is radiated emission and this is conducted emission. So according to CISPR, the resolution bandwidth for the measurement frequency of 150 kilohertz to 30 megahertz in case of conducted emission should be 9 kilohertz, and according to FCC, the measurement frequency of 30 megahertz to 1 gigahertz for radiated emission, the resolution bandwidth should be 120 kilohertz. So if you match it with the given option, the correct option is option D. I hope this is clear. If you have any doubt in this, please let me know. Yeah, so if it is clear, then we will move on to the next problem. In question 2 is a microwave device has two subsystems operating at different clock frequencies. A spectrum analyzer is measuring the radiated emission from this device. Determine the difference in the measured signal level if the upper bound of the measured signal is 3.875 decibels. So in the problem it is given that there is a microwave device. It has two subsystems operating at different clock frequencies. So let's say there is a system, some microwave system. Maybe let's say it's a power amplifier or it's a signal generator which generates microwave frequencies. So let's say this is a power amplifier, microwave power amplifier, which has a two component signal generator which generates that microwave signal, and then there is an amplifier, second module. This is first, just one example that I am giving just to explain this. And they are connected, interconnected definitely, because the part of this thing is to generate the signal, and the second part is that amplifier which amplifies the signal. Maybe here it is a 0.5 watt signal, and then at output we want, let's say, some 100 watts of microwave signal, let's say some frequency 1 gigahertz. Now what is happening is a spectrum analyzer is measuring the radiated emission from this device. So maybe the shielding is not proper, or there is some faulty devices in 1 and 2 module, submodule 1 and subsystem 2. So there is some radiated emission coming out from both subsystem 1 and subsystem 2, and we are using one spectrum analyzer to measure the radiated emission from this device. And we have to determine the difference in the measured signal level if the upper bound of the measured signal is, so they have already measured the signal and the upper bound is coming out as 3.875. So what is given is upper bound of the measured signal is given as 3.875 decibel. And what is upper bound is? Upper bound is defined as, so I am going slowly so that you guys can also solve this if you already know the answer. So the upper bound is defined as the relative increase over the larger of the two signals. Increase over the larger of the two signals. So what it means is, let's say one signal is larger and the second one is smaller, and whatever the difference between them is the upper bound. So relative increase, like how much the larger signal is greater than the smaller signal. So that relative increase in decibels is upper bound. So it is given in decibels as 3.875 decibels. And we already know that relative increase R is given by relative increase, or we can say upper bound relative increase. Here we are denoting it as R. In decibels, it is given by this formula. R is equals to 20 log 10, so log base 10, 1 plus 10 to the power minus y by 20, where y is the difference in the measured signal level. So that's what we have to find out. This y only is what is needed in the problem. So this y is the difference in the measured signal. Measured signal level. So R is given as, in the question it is given as 3.875 dB, and the formula for R we already know, so we can just equate these two. 3875 is equals to 20 log 10, 1 plus 10 to the power minus y by 20. So now we want to find out what y is. So I will bring this 20 on this left hand side, equals to log base 10, 1 plus 10 to the power minus y by 20. Now we will take in order to remove this logarithm on this RHS, what I am going to do is we can, just a second, so we can put it as 10 to the power 3.875 divided by 20. Since the base of that log was 10, so if I take I will write in as 10 to the power log something, right? So what it gives, whatever this x is. So this is just for example, but in our case it is sorry. Yeah, so what I was saying is, so in order to remove the logarithm from the right hand side, I am taking everything as 10 to the power 875 divided by 20 is equals to this log. When I'll do this on the right hand side, the log will be removed. So what we will left with, 1 plus y to the power minus, sorry, 1 plus 10 to the power minus y by 20. So when I solve this 10 to the power 3.875 divided by 20, I will get 1.562, and this minus 1 comes from RHS. So here I will have minus 10 to the power y by 20. Just a second. So here we will left with 562 is equals to 10 to the power minus y by 20. Now in order to remove this 10 to the power, because we have to find y, right? So what I can do is I can take logarithm on the both sides. So when I take log with base 10 of 0.562 and also log of 10 to the power minus y by 20, what I will get on this side is minus y by 20, and log of logarithm of 0.562 is minus 0.25. So when I solve, and the answer will be in decibels, because this 3.875 was still in decibels. That's how we equate it to this, right? So the final answer will also be in decibels. So y will be 0.25 multiplied with 20, and we get something 5.0014 decibels. Or I can simply write this as, because this is not 0.25, something else is also there in some decimal points. So the final answer is, we can take it as approximately equal to 5 decibels. I hope this is clear. And if you match it with the given options, so here the correct option is option C, 5 decibels. So if you have any doubt in this problem, please let me know. So if it is clear, we will move on to question number 3. Question 3 is, which of the following condition is desirable for a peak detector? Where capital T is the period of the spike and R and C is the resistance of that resistor and capacitance of the capacitor. So peak detector, you have seen in the lecture how it looks like. It's a device which consists of a diode, a resistor and a capacitor. Sorry for the noise. So, sorry. So, what I was discussing about is, we were discussing question number 3, which of the following condition is desirable for a peak detector? So, first I am drawing the circuit diagram of a peak detector. This is what a peak detector is. So, here a diode is there. It's a normal diode. So, this is our R and this is C. Here our will be input and this will be V out. So one desirable condition should be the time period of the some signal which is coming of the clock signal. Let's say if it is like this, let's say it is a sinusoidal signal. So this is our time period T. So what it should, and if we see that that time constant of a peak detector is RC. So according to regulatory bodies, the period of spike should be greater than the time constant of the peak detector. So the time constant is RC, and according to regulations, this time period of those peaks which are coming should be, if some, that's what was discussed in the lecture, right? Let's say some peaks are coming. So if these spikes are regular or means periodic, then it is of concern for EMI EMC. But if some peaks are happening, like spikes are happening randomly in some signal, like these kind of things which are random, are not periodic, then we are not concerned about those. We are concerned about the spikes which are periodic, and according to the regulatory bodies, the period of the spike should be greater than the time constant of the peak detector. So the time period T should be greater than RC. So a quasi peak detector or an average detector is preferable. So this T should be greater than RC, and if we check for the options, the correct option is A. If you have any doubt in this, please let me know. I will just write down what I told you. So according to regulatory bodies, like FCC or IEC, what is the period of pipe should be greater than the time constant of the peak detector. So that's why the answer was time t should be greater than RC. So this is the period of the spike and RC is the time constant of our peak detector. Maybe like we denote it as tau. So I hope this is clear. We will move on to question number 4. Consider the following statements for a Hertzian dipole. Hertzian dipole means that current element that professor has discussed. So first we can read out what are the three statements are. So three statements are given related to a Hertzian dipole. So far field is inversely proportional to the distance of observation. Statement B is far field is directly proportional to the length of the element and inversely proportional to the current. Statement C is far field is directly proportional to the sine of the elevation angle. So we can see this all the statements are related to the far field of a Hertzian dipole. So first we will write down the formula for electric field of a Hertzian dipole at a far field. It's given by E is equals to Em by 2. So Em by R sine omega of t minus r by c unit vector, because it's directed along the theta direction, and Em is given as frequency f into mu naught. Mu naught is permeability of free space. Mu naught is 4 pi into 10 to the power minus 7 divided by 2. I tilde, that means the phasor, into dl is the length of that current element or the Hertzian dipole multiplied with sine theta, and theta is the elevation angle. So if we can see this here is the fields are proportional to the far field is proportional to
Excuse me, sir.
yes.
Just a point in for the previous question.
Yes.
Uh, wouldn't I just had a doubt that wouldn't the upper limit for the RC
Yeah.
will get the smooth output if the RC is larger than the T?
Yeah. So whole idea is we don't want to detect like we just want to detect the peaks. We don't
Yeah,
want. Yeah.
but you told that the T will be larger. The answer was the T will be larger than RC.
Yeah. So we have to select such a components, like the values of R and C should be such that this time constant should be greater than, like the moment it gets charged, this capacitor gets charged, it
Uh-huh.
should be able to should not be able to completely discharge. Like it should be able to completely discharge before the next peak comes. We don't want to have that to happen.
Okay. So for that, isn't the doesn't the RC needs to be larger than the T?
uh, no, I don't think so. That's if I draw a signal and let's say this R and C is a time constant, which is tau is
Okay.
equals to RC.
Okay.
So ideally it should be small only. So maybe I am wrong, but that's what according to this.
Hmm.
I just went through the regulatory bodies and what they are saying. But yeah,
Okay.
maybe I'm not able to explain it very well. But whatever the answer is correct only. It should be
All
greater
right.
than the time period of the peak should be greater than RC.
All right. All right.
Okay,
Thank you.
next lecture I will try to explain it in a better way, but I'm not sure like why. I'm not
Sure.
able to explain it very well.
All right, no,
Oh,
no problem.
okay, yeah, yeah, thank you. So the fields, what we are discussing in the fourth question is the three statements are given related to Hertzian dipole. So and all these statements are corresponding to, they are referring to the far field of that dipole. So I started with writing the formula for E field at a far field for that Hertzian dipole. So this is the formula, and it's asking about proportionality. So we can just find out what are the things which are proportional to the field. The fields are proportional to 1 by r. That means it's inversely proportional to the distance. So it's proportional to 1 by r and directly proportional to the current and the length of that Hertzian dipole or the current element, and also it is directly proportional to sine theta, sine of that elevation angle. So this is the inference that we have made from the formula for electric field. We could have written the H field also, but the proportionality will remains the same. That's why I put the E field formula here, and we can see the first statement is far field is inversely proportional to the distance of observance. This is correct because it is proportional to 1 by r. That means it is inversely proportional to the distance, which is r. So statement A is true. Statement B is far field is directly proportional to the length of the element. Yes, it is directly proportional to the dl. And it's saying and inversely proportional to the current. No, it's directly proportional to the current. So if the current increases, this E field intensity will increase. Means it is directly proportional, not inversely proportional. So statement B is not true. And statement C is far field is directly proportional to sine of the elevation angles, means sine theta. So here it is directly proportional to sine theta. So statement C is also correct. So if we match the given options, so both statement A and C are correct. So option C is correct. So I hope this is clear. If you have any doubt in this, please let me know. So if this is clear, we will move on to question 5. So here question 5 and 6 has a common data. So, so means they are referring to the same Hertzian dipole. So question is a Hertzian dipole antenna has a total length of, so in the problem we will note down what is given. So dl is given as 5 centimeter. So I will directly note it down as just what I'm doing here is I'm just noting down what are the quantities which are given, and current is given as 3 amperes, and it's operating at a frequency f is given as 1 megahertz. And in question 5 we have to determine the electric and magnetic field at a distance of 2000 meters at an angle of 45 degree. So what's the question is asking is we have to find the electric and magnetic field intensities uh, at a distance of 2000 meters or 2 kilometers. So our first step should be we have to find out this 2000 meters lies in the far field or the near field of that Hertzian dipole, and theta is given as 45 degrees. So first of all we will find what is dl by lambda is. So lambda we can find out because we know what the frequency is 1 megahertz. So lambda is given by c by f, where c is light speed of light, speed of that electromagnetic wave in vacuum, and frequency is given as 1 megahertz, so 10 to the power 6. So lambda is around 300, yeah, it's 300 meters. So if we find dl by lambda, am I audible? Okay. So dl by lambda we have to calculate. 5 into, so dl means the length of the element. This is 3, so dl is given as 5 centimeters, so I will write it in meters. So 5 into 10 to the power minus 2, and lambda is 300 meters. So if we calculate dl by lambda, it comes 1 by 6000, which is much less than 1 by 10. So the element is a current element, and for far field r should be greater than 3 lambda. And in this case, first we will calculate what is 3 lambda. It should be 3 lambda should be 900 meters, but for us in the question r is given as 2000 meters. So since this r is greater than 3 lambda, definitely we have to calculate in the far field. So here now for in the far field only we have to calculate theta, e theta and h phi. We can neglect other components because they are not significant. So e theta is given by e theta is given by j f mu naught by 2 ideal sin theta into e to the power minus j beta naught r by 2, beta naught r by r. So from this we can calculate what is e theta. Yes ma'am. Hello. I just try to reconnect. I thought some issue was there with my. So you were able to hear when I was explaining the question number 5, right? So if you have any doubt in question number 5, please let me know. So in this problem, a dipole, Hertzian dipole was given, whose total length of that current element was 5 centimeters, and a current of 3 ampere was flowing through it, and it was operating at a frequency, and the current's frequency was 1 megahertz. So now we have to determine the electric and magnetic field at a distance of 2000 meters and at an angle. So let's say if that current element was somewhere here. This is our current element, and at a distance r, which is 2 kilometers, at this point P, we have to find the E field and H field. So and the elevation angle was theta, which is 45 degrees. So this is what we have to find it out. First we have to find out if this point P lies in the far field zone or near field zone of this current element. So that's what we have done here, and we have calculated E field and H field. Now in the question number 6, we have to find, for the same Hertzian dipole, we have to determine the average power density at a distance of, so now here R is 2100 meters, and it's asking the direction of maximum radiation. So if we see the formulas of E and H, so they are dependent on this theta by sine theta, and we know that sine theta will be maximum as 1, and 1 theta will be 90 degrees. So this is the angle of maximum radiation, theta is 90. So direction of maximum radiation is theta as 90 degrees, and average power density S average is, so I am denoting average power density as S average, SAV, average power density. Average power density is given by, for the Hertzian dipole, is 15 pi dl by lambda whole square into I by root 2 whole square sine square theta by r square, and when we calculate it, we will get 15 pi into dl, same, the antenna remains the same, so dl is 5 centimeters, 5 into 10 to the power minus 2 whole square, current is 3 amperes, so and square, and sine square theta, which is sine square 90, divided by lambda is 300 meters, so lambda square, into under root 2 whole square becomes 2 here, and multiplied with r square, where here r is 2100 meters, so r square. So when we calculate this, we will get 1.3357 into 10 to the power minus 12 watt per meter square, or I can because in the options everything is in nano or picometers, so 10 to the power minus 12 means picometers, so 1.3357 pico watt per meter square. Now we match with the given option, and the correct option is option B. I hope question 6 is clear. If you have any doubt in this, please let me know. So if it is clear, then we will move on to question number 7. Consider a Hertzian dipole of length. So here this dipole means Hertzian dipole or the current element. Length is given as TL is 1 centimeter and it's carrying a phasor current. So I tilde is given as 2 with angle 30 degrees and it's operating at a frequency of 100 megahertz, or I can write this as 10 to the power 8 hertz. So we have to determine the elevation component of the electric field at a distance of 10 centimeters away from the dipole, and theta is 30 degrees. So here R is given as it's only 10 centimeters, and we will calculate the wavelength, which is c by f lambda. So 3 into 10 to the power 8 by 10 to the power 8. So lambda is 3 meters. So for this dipole, the lambda is 3 meters and R is given as 0.1 meter. So we see if here R is less than 3 lambda. So the point of observation is not in the far field. Not in the far field region. Therefore we cannot neglect the 1 by r square and 1 by r cube term in the electric field formula. So in the formula there are three terms: 1 by beta naught r, 1 by beta naught square r square, so beta naught square, and beta naught cube r cube. So these terms we cannot neglect here. So what we have to do here is, first we will, because since they are not in the far field, they are in the observation point is in near field, so we have to use the whole formula. We cannot neglect these terms. So we'll start with calculating what is beta naught square r square is. Sorry, we will first calculate what is 1 by beta naught r is. When we calculate, it comes out to be 4.774, and 1 by beta naught square r square is 22.8, and next term will be beta naught cube r cube. It will be 108.85. So I will note down the formula here. E theta is given by IDL beta naught square sin theta divided by 4 pi into J 1 by beta naught r plus 1 by beta naught square r square plus, sorry, this is minus here, minus J 1 by beta naught cube r cube multiplied with e to the power minus j beta naught r. So now when we calculate it, we get, so we know what is I is given as 2 into with angle 30 degrees as in a phasor form, and dl is 1 centimeter into eta naught is 125 for free space, and beta naught comes out to be 4 pi square, and sine theta is given as 30 degrees divided with 4 pi, and these values we have already calculated. What is 1 by beta naught r beta naught square r square, and 1 by beta naught cube r cube. So I will just directly note down these values here. 4.774 plus 22.8 minus 108.85, and e to the power, so in multiply it, so I didn't have the space, so that's why I'm writing it like that. So e to the power minus j 0.2 pi by 8, so pi by 3, sorry. So when we calculate this, we will get e theta as 140.2 with angle minus 59.64 degrees, or I can write this as approximately equal to 140, and 59.64 I can take it as 60 degrees, minus 60 degrees. So this is the E field component, and in the problem we have to determine the elevation component of the electric field. Elevation component means we have to find the E theta, because theta is our elevation angle. So we have to find elevation component of the electric field, E theta. So first what we did is we find out what is the observation point, where is the observation point, and we find out that r is less than 3 lambda. That means the point of observation is not in the far field region, and therefore we were not able to neglect the terms beta naught square by r square, and means we were not able to, we should not neglect 1 by r square and 1 by r cube terms from the formula. And when we calculated, we got e theta as 140 with angle minus 60 degree. So the correct option is option B. I hope this question is clear. If you have any doubt in this, please let me know. If question 7 is clear, we will move on to question number 8. Question number 8, the same, whatever the dipole we have used in the previous question, same Hertzian dipole is there with 1 centimeter length, carrying the same current and the same frequency. So here we have to compute E theta by h phi. Like we have to compute the ratio of these magnitude. So first, because you already know what E theta is, you have to calculate h phi. So which is given by IDL beta naught square sine theta divided by 4 pi into j 1 by beta naught r plus 1 by beta naught square r square. So here, because this observation point is in near field, we are not neglecting 1 by r square term, same as previous problem, into e to the power minus j beta naught r. And when we calculate this, I know what I is, it's given as, and dl is 1 centimeter, and beta naught 4 pi square into sine 30 degrees divided by 4 pi into 3 square to 4.774 j plus 22.8 multiplied with e to the power minus j beta naught r, which is 0.2 pi by 3. So when we calculate this, we will get HV as 0.0813 angle. So I'm writing it in the phasor form. So the angle comes out to be 29.83 degrees. And we just have to take the ratios of the magnitudes, means, so this is the magnitude, so we have to take the ratio of E theta and HV. So E theta by HV is given by 140.2 divided by 0.0813, and when we do this division we will get 1724, and when we match it with the given option, the correct option is option B, 1724. I hope the question is clear. If you have any doubt in this question number 8, please let me know. So if this is clear, we will move on to question number 9. In question number 9, a Hertzian dipole is radiating in free space. The measured electric field is 0.25 millivolt per meter at a distance of 150 meter away from the antenna. We have to determine the value of the electric field at a distance 250 meter if the dipole is operated at a frequency of 10 megahertz. So in the problem, what is given as a Hertzian dipole is given, which is radiating in the free space, and we have measured the electric field at a distance. Let's say this is as d1, and what are we measuring here is electric field ED1, which is given as 0.25 millivolt per meter. So in the problem, d1 is also given as 150 meters, and at that distance we are measuring electric field. So I'm denoting it as ED1 0.25 millivolt per meter. And what they are asking is, they are asking what will be the E field at a distance d2, which is 250 meters. So at 250 meters, what will be the value of this ED2? So first we will check if these points d1 and d2, these observation points, are lying in the far field or not. So for that we have to first calculate what is the lambda. So which is 3 into 10 to the power 8 divided by 10 to the power 7, because 10 megahertz, right? So when we solve this, we will get 30 meters. And what will be the 3 lambda? Like generally we take this for the Hertzian dipole, if the observation point is greater than if this r is greater than 3 lambda, then that observation point is in far field. So here what is happening is, our d1 is 150 meter, and 3 lambda, if we calculate, since our lambda is 30 meters, so 3 into 30 is 90 meters. So here we can see d1 is greater than 3 lambda, and definitely d2 is also greater than 3 lambda. So both these points are in far field. So the distance measurement is in so the distance of measurement is at far field, and we know that the formula for that is, since both are inversely proportional to the distance, we can just directly, because we are using the same antenna here, so, and we can use this proportionality. So ED2 and ED1, the only thing is changing, if we write down the formula for ED2 and ED1, the thing which is changing is the D or the R. and since they are inversely proportional, I can write this as, so ED2 by ED1 is equal to D1 by D2. And since we know what is this electric field at D1 is, and we have to find the magnitude at D2, I can modify this formula like this: ED1. So now I can easily calculate what ED2 will be. Since I know what is D1, D1 is 150 meters, D2 is 250 meters, and ED1 is 0.25 millivolt per meter, and when we calculate this we will get 0.15 millivolt per meter. So this is the magnitude of the electric field at distance 250 meters for the Hertzian dipole. So if you match it with the given option, the correct option is C, 0.15 millivolt per meter. So I hope question number 9 is clear. If you have any doubt in question 9, please let me know. If it is clear, we will move on to question number 10. So here instead of a Hertzian dipole, we have a half wave dipole. So a different antenna is operating, means a half wave dipole is operating at a frequency of 300 megahertz, and the input current to the terminals is 20 milliamperes. We have to determine the average power density and the average power radiated at a distance of 50 meters in the broadside direction. So everything else is clear, but it's asking about this broadside direction. So broadside direction means theta is 90 degree. This is the broadside direction. And the frequency f is 300 megahertz, and the distance of measurement, the observation distance is 50 meters. And one thing is missing in the problem is the radiation resistance R of the antenna is 73 ohms. So this should have been given. So from this we can calculate what will be beta R, which is beta is nothing but 2 pi by lambda, and R is the distance, which is 50 meters, and when we calculate this we will get 100 pi. So beta naught R is 100 pi. So now I am calculating the field of dipole antenna, half wave dipole antenna, when theta is 90 degrees. So f theta is 90 degree is cos so half wave dipole means the length of this antenna will be lambda by 2. So this dipole length will be lambda by 2. That's why we are calling it half wave dipole. So and the lambda by 2 will be 0.5 meters. So f at 90 degree is given by cos of beta L by 2 cos theta divided by sin theta. So here I am directly taking the formulas, I am not deriving it, but if you want the derivation, you can refer to any antenna theory textbook. because I think those formulas won't be discussed in the course. I think professor has also derived the formulas but didn't explain it because he has referred to the antenna theory lectures. So we can directly write down the formula as pi. I'm just directly writing it as cos pi by 2 cos 90 divided, theta is broadside, so theta is 90 degrees, sin 90 degrees. And when we calculate this, we will get 1, because cos 90 is 0 and cos 0 is 1 and sin 90 is 1. So, and for half wave dipole, E theta is given by J60. So I'm directly writing the formula for a far field region at E theta for a half wave dipole antenna is given by J60 I into e to the power minus j beta naught r by r into f of theta. So we have already calculated this f of theta. So when you substitute these values, we will get 60 into 20 into 10 to the power minus 3 into e to the power minus j 100 pi divided by r is 50 meters. F theta came out to be 1 when theta is 90. So E theta is j 0.024 into cos of 100 pi minus j sin 100 pi. So I'm just writing this e to the power minus j 100 pi as this cos 100 pi minus j sin 100 pi. So when you calculate this, the magnitude will be 0.024, which I can write this as 24 millivolt per meter. So and then we have also calculated the average power density. So average power density as average is given by E theta square by 2 eta naught. So E theta square, we just find out what is the magnitude of E theta is 0.024, to take the whole square. And since the antenna is radiating in the free space, so the radiation resistance of free space is 120 pi. 20 into 120 pi, so 2 into 120 pi, and when we calculate this, it comes out to be 0.764 micro watt per meter square. And P average is given by radiation resistance of the antenna into Im, magnitude of the current, and divided by 2. So R radiated should have been given in the problem, but it was not, so it should have been given as 73 ohms. 70 73 into 20 into 10 to the power minus 3, so the current is given as 20 milliamperes whole square divided by 2. And when we solve this, we will get P average as 14.6 milliwatt. And if we match it with the given options, so the correct option is option A, 0.764, and P averages 14.6 milliwatt. So in the problem we have to find the average power density and the average power radiated at a distance of 50 meters in the broadside direction. So broadside direction was when theta is 90 degrees. I hope this is clear. If you have any doubt in question number 10, please let me know. And I would request you to go through the textbook also. Just once read through the corresponding sections. I think right now whatever the lectures are being covered are from chapter 3 of the textbook. So please go through that also if you have time. And if you have any doubt in that also, you can try solving the exercise problems in the textbook. So if you face any problem in that, you can email me at my email ID is, I'm just noting down my email ID is ed22d009 at the rate smail.iitm.ac.in. So this is my email ID. I will type it here. It's 22d009 at the rate smail.iitm.ac.in. You can email me if you have any doubt in the problems that we have solved today, or any problems from the exercise in the textbook. That's all for today. If you have any doubt, please let me know. Otherwise, that's all from my side for today's session. Thank you for joining. Okay, thank you. So if you have any doubt, you can ask me, or uh, Rabinder Singh, whatever you are asking, I will discuss in the next session. So I will get back to
Okay.
you.
Okay, sir. Thank you.
Thank you. Thank you for joining, everyone. Thank you.